Okay, so now after talking about the generic result, okay, or generic definition, now let's come to an example of two discrete random variables. And this, if you recall, was one of the examples in the first lecture of the semester that I talked to you about, right? Draw two socks at random without replacement from a drawer full of 12 color socks. There are 6 black, 4 white, and 2 purple. Okay, we use capital B represent the number of black socks, and capital W represent the number of white socks drawn. Okay, then the distribution of B and W, okay, are given by, so let me just show all of the probability calculation that we had done before. Okay, so back then you're able to, I think, yeah, many of you were able to do it in the first lecture just by going through the logic and then the calculation step by step. Okay, but then of course, now we have learned a lot about, I guess, combinatorics, right? Like combinations, permutations, and then probability in particular, I guess, events of equally likely outcomes, right? So because of all that, all of these results that we're showing up here can be summarized, okay, by this general statement down here, okay? So we also talked about this, if you vaguely remember, in the first lecture, but don't worry if you don't remember about the detail, but now let's make sure that we understand what this is doing. Okay, so this is giving us a generic expression, right, of the probability of B equals to K. And don't forget, you're only drawing 2 socks in total, right? So in order to get the probability of B equals to K, where K can be 0, 1, 2, what we're doing is that so the denominator, right, is the total number of ways of drawing 2 socks out of the 12 socks. So there's no restrictions at all, and we're dividing it because it's equally likely outcomes, right? So that's the total number of possibility. And then in the numerator, what we're doing, right, is a product, right, of getting K black socks out of 6, right, and then getting the remaining 2 minus K socks from the remaining 6 socks, 4 white and 2 purple. Okay, so that's why. Well, again, because you need to multiply them in order to get the total number of ways to get 2 socks in total, right? So you have this ratio going on to represent the probability. In this case, the marginal probability of B equals to K. Okay, only about one variable at a time. Okay, so similarly, you can work out this expression for W as well. It's slightly different, even though the denominator is the same, but the numerator is different because of the total number of different color socks are different over here. Okay, but overall, I'm sure you should be able to convince yourself that this is true. Okay, so all right, so that's all good. All of this that we have done is similar to what we already knew, right? We know if I'm only curious about each variable at a time, I'm able to use this general expression for each to come up with that, what we mean by the marginal probability. Okay, we're going to define those terms again, but marginal is, as we were using over here, is talking about one variable at a time. Okay, but of course, if you remember, the topic of this lecture is about joint distribution. Okay, so now let's come to a new table. Okay, in this case, now instead of only looking at B and W separately about they're taking 0, 1, 2, we're looking at what we mean by joint. Okay, we're looking at, as you can see the notation here, okay, I'm using, so it's PMF, right, because it's discrete random variables here, so I'm using P, okay, to represent the PMF. But as you can see, again, we are using subscript, okay, B comma W, both capital letters, to represent is the PMF of these 2 random variables, okay? And then we have, of course, small b and small w over here represent, so this notation represent the probability of capital B equals to B, and then capital W equals to small w. Okay, so in here, again, because we're working with discrete random variables, it's, well, the probability of the random variable taking a particular value could be non-negative, right? It could be positive, okay? Unlike the continuous case, the probability of the random variable taking any particular value is 0. You only get the probability after you do the integration. But here we do have a specific probability that could be greater than 0 when you're working with this. So now let's come back to this work and then figure out if we can fill out this table a little bit, okay? So each of the cells, so like this one, the 3, I guess 3 by 3, 9 over here, all of this 9 cells, they are the joint, okay? It's the joint probability of, like, saying this one will be like W equals to 0 and B equals to 0, right? And then this one will be about W equals to 1 and B equals to 0. Okay, so this is what we mean by this table. And then for discrete random variables, both of them discrete in this case, B and W. So it's pretty straightforward to come up with the table like this, and then we work out the probability one by one. Okay, so let's start doing that, and then feel free to also try it out before you continue the video. And so let me get to the first one. Okay, so the first one, right, is B equals to 0 and W equals to 0. Okay, the probability is 1/66 because you will have to choose both of them to be purple, right? So I guess one way you can do it is that you're gonna get because you're gonna get both of them to be purple. So if you work out the math, I think you will figure out that this is 1/66. Okay, so you can always, of course, use the ratio notation that we have doing. So it's 12 choose 2, right? That's the total number of ways, so it's choosing any. And I think there's only one way, right? You can choose 2 purples, is 2 choose 2. And I think that gives you 1/66. Okay, so that's how you get the first one. Okay, and then of course you're gonna continue doing all of them one by one. So let me just maybe clear this and then go about one by one. Okay, so the second one, okay, this particular one, okay, if you look at the table here, it's talking about B equals to 0 and W equals to 1. Okay, so B equals to 0, W equals to 1. What can we do? We can do, so again, the denominator is 12 choose 2. That's never changed. Okay, and the numerator, okay, let's see. B has to be 0, right? White, and then W has to be 1. So that's the same. That's 4 choose 1 to get the white, right? And then we have to do 2 choose 1 over there. Okay, so again, this, if you do the math quickly, it's going to be 8 in the top, on the top, and then 66 in the bottom. Okay, so that's why it's 8/66. Okay, so I won't, I guess, just for the interest of time, I won't like walk through each one one by one, but I do want to show you that if you follow the same logic, you will be able to get all of this. Okay, and if you actually continue doing especially this 3 over here, I want to highlight because if you look at this particular case, like the probability of 0 is because, well, you can never get 1 black and 2 white, right? Because the total number of socks you're drawing is 2. So this case, and this case, all of them are going to be 0. Okay, whereas the other ones, you can work it out. Okay, so hopefully that makes sense. Okay, and then I will just also highlight that, well, we are able to come up with expression for this seemingly complicated scenario here. Okay, so let me show you this joint distribution. Okay, how can I express the joint distribution? Okay, the joint distribution, so earlier, like I worked through the 2 with everyone here, but then I asked you to do the remaining, so hopefully you get a chance to do it. But if you do it one by one, you realize that they follow a general trend, right? The numerator, the denominator is always 12 choose 2, because that's the total number of ways you're able to choose 2 socks, right? And then if I define B equals to B, right, W equals to W, then the numerator, the way that I can get B black socks and W white socks will be exactly 6 choose B, because I have 6 black socks to choose from, right? 4 choose W, right? Because I have four white socks to choose from, and then eventually also 2 choose 2 minus B minus W, because this 2 is the 2 purple socks that we have, right? And then this 2 is the total number of socks, which is 2 that we're drawing from. So because there are B black socks, W white socks, so the number of remaining socks that could be purple is 2 minus B minus W. Okay, and of course, don't forget, right? We clearly define the range of the B and W in this case. Okay, so B needs to be between 0 and 2, inclusive, W as well, but also, right, B plus W needs to be smaller or equal to 2. Okay, so that's why, as you can see, for these 3 cases up here, okay, it's already beyond this particular range that we're working with. So it's going to be reduced to 0 for every case, okay? But just like we talked through just now, it's going to be 0 no matter what, because of the definition or how the exercise is set up, okay? Lastly, I would just say that, well, one way to check if your work is right about all of this little probability, the different 6 over here, is to check if they add up to 1, okay? Because they should, okay?